So hi friends, welcome back to my YouTube channel Chemistry Basics. So let's start the amines part 2. So we are now going to take the preparation and reactions of amines. So how amines are prepared? So first method is from alkyl halides. So for that you have to take the alkyl halide and react with the alcoholic ammonia in a sealed tube at higher temperature, so 373 Kelvin. In this particular reaction, you will get the mixture of all type of amines with the quaternary ammonium salts also. So you will get the primary amine, secondary amine, tertiary amine as well as quaternary ammonium salts also. So as you are getting the mixtures, it is difficult to separate them, and therefore this is not a good laboratory preparation. And hence this particular method is usually employed at industrial level, where the treatment of the base is given to that all amines and separated by fractional distillation method, so where you can easily separate all that mixture into a individual amines, that primary, secondary and tertiary amines. Let's see the examples. So here we have taken the ammonia and alkyl halide is taken here methyl iodide. So simple, just a substitution reaction takes place here, or that nucleophilic attack of this lone pair of nitrogen takes place on the electrophilic methyl group, and iodine is removed as a leaving group, and you will get the methyl ammonium iodide. This is the ammonium salt, which further on aqueous basic workup you will get the methyl amine here. Simply basic treatment is given to that OH minus will picks up the proton from this NH3 plus or ammonium group to form a amine. Similarly, if you are taking a primary amine and repeating the same procedure, product you will get here dimethylamine. Simply here, instead of ammonia, here is the amine. Here is the lone pair that can be attacked on this methyl. Again, iodine is a good leaving group, so it will give the dimethyl ammonium iodide, which on further aqueous basic workup, so you'll get the dimethylamine here. Similarly, dimethylamine when treated with a alkyl halide, so you'll get the product trimethylamine. So in this way you can prepare all that amines here, and if you're taking the trimethylamine, you'll get the tetramethylammonium hydroxide in that. So this is the mixture of the products you are getting in this particular reaction. Now let's see the second preparation of amine, that is from alcohols. So from alcohols also we will get the amines here by using ammonia again. So when vapors of alcohols and ammonia are passed over alumina at 400 degrees Celsius, so mixture of primary, secondary and tertiary amines are formed again. Let's take here some ethanol and the ammonia. So simple dehydration will take place here. Water molecule is eliminated and methyl group will join to NH2. So you will get here methylamine. Further, this methylamine can react with the next mole of methanol here. So you will get here again dehydration. So OH and second hydrogen of this NH2 group will be replaced here now. So by this methyl group, and you will get dimethylamine. Similarly, this dimethylamine again react with the next mole of methanol, and you will get the trimethylamine here. So that is the mixture of primary, secondary and tertiary amines are formed in this method also. Third is a reductive amination of aldehydes and ketones. Reductive amination of aldehydes and ketones. Name itself suggests that two reactions are occur in this particular preparation. One is reduction, another is amination. So reduction is latter. First you have to do the amination. So amination and then followed by the reduction, then you will get the amines here. So let's take the any aldehyde or ketone here in carbonyl compound, and when you are reacting with the ammonia, so simply dehydration will take place. So oxygen from the carbonyl and two hydrogens from the ammonia, they will be eliminated as a water, and this NH group will join to this olefinic carbon, and you will get here imine product. So C double bond NH, imine, which further undergo reduction in presence of nickel catalyst. H2 will just adds across the carbon nitrogen double bond and convert it into a saturated compound, that's the primary amine. Similarly, instead of ammonia, if you are taking the primary amine and reacting with the aldehyde or ketone, you will get the imine again, and on reduction you will get the secondary amine. If secondary amine is reacted with aldehyde or ketone, so obviously further reduction of that iminium ion will give you the tertiary amine. So reductive amination of aldehydes and ketones also gives you all type of amines, that's a primary amine, secondary amine, as well as tertiary amines, and these are the examples that will tells you how you are getting the different amines here. So here we have taken the acetaldehyde, ammonia. So simply dehydration, you will get the imine here, which further reduced to ethylamine. If you are taking the ethylamine and reacting with the acetaldehyde, so you will get this imine, which reduced to diethylamine here. And if you are taking the dimethylamine on reaction with the acetone, you will get this iminium ion, which further reduced to final, that's a dimethyl isopropylamine. So if you see here, nitrogen is attached to three alkyl groups, this is the isopropyl group, and two methyl groups here. So this is the tertiary amine. So primary, secondary, and tertiary, all three types of the amines are prepared by this method, that's the reductive amination. Next is preparation of amines by Gabriel thalamide synthesis. So Gabriel thalamide synthesis is a very important reaction. So this method used for the preparation of primary amines from thalamide and alkyl halide. So that's the first thing about this Gabriel thalamide synthesis. A raw material is thalamide and alkyl halide. So thalamide on treatment with alcoholic KOH forms potassium salt of thalamide, which further reacts with alkyl halide to give N-alkyl thalamide. And finally, this N-alkyl thalamide on alkaline hydrolysis forms primary amines, and potassium thalate is a side product or byproduct. So by this Gabriel thalamide synthesis, secondary and tertiary amines are not prepared. Remember, that's a very important thing. Secondary and tertiary amines are not prepared by this method. Primary aromatic amines also not prepared by this method. So last 2 points are important. Secondary and tertiary amines are not prepared by this method, as well as primary aromatic amines are also not prepared by this method. Let's see the Gabriel thalamide synthesis. Here is the example. So we have taken the thalamide in basic medium, so that OH minus will picks up this acidic proton. So after deprotonation, breaking of this NH bond, so whatever conjugate pace you are getting, that will be the well stabilized due to the resonance, and therefore this proton is an acidic proton. So thalamide on reaction with base forms potassium thalamide, as we are taking the KOH. Next, this potassium thalamide is now a nucleophile. It will act as a nucleophile and reacts with the alkyl halide to follow the SN2 route to form N-alkyl substituted thalamide. So this is the N-alkyl thalamide. And now finally it will undergo the hydrolysis in basic medium. So simply these amide groups are going to be hydrolyzed. These amide bonds CON and CON, these bonds are breaking to form a amine as a product. So this part is removed, NR part is removed as amine, and you will get the potassium thalate as a side product. So this is about the mechanism of this reaction. That's a Gabriel thalamide synthesis. It is Hofmann-Bromamide reaction or Hofmann-Bromamide rearrangement. So in this reaction also we can prepare the primary amine from amides. So in this reaction an amide is warmed with bromine or sometimes chlorine you can take in presence of aqueous base like KOH or NOH to form a primary amine. This reaction involves formation of nitrene intermediate, that is the very important intermediate in this reaction that involves the rearrangement. Now in this Hofmann-Bromide reaction, if you compare the reactant and product, so product having one carbon less as compared to reactant, and therefore this is an example of step down reaction. So as in this reaction carbonyl group is removed, and hence this reaction is also called as a Hofmann degradation reaction. This is the general example. If you are taking the amide and reacting with a bromine in presence of basic medium, there is a formation of amine with the elimination of sodium carbonate, sodium bromide and water. Let's see the mechanism of this reaction. The very first step, that bromine when reacted with a base, it forms a sodium hypobromide. In sodium hypobromide, we know that the polarity, so halogen or bromine is having a delta positive charge, and while oxygen is having a delta negative charge, as oxygen is more electronegative than bromine. And that's the important sodium hypobromide in this particular reaction. So initially that primary amide on reaction with base, there is abstraction of this acidic proton. So to form this alkoxide ion, or you can say anion, this anion has this enolate type stability. And this alkoxide ion further attacks on this sodium hypobromide, preferentially on that bromine as it's having a positive charge. And it will attach to the nitrogen here to form N-bromamide species. Now as if you see here, this nitrogen is surrounded by the electron withdrawing carbonyl group, electron withdrawing bromine, it's electronegative, and therefore this hydrogen now becomes more acidic. So second mole of base that will picks up this proton and to form anion here. That anion is known as a N-bromamide anion. This N-bromamide anion is very unstable as the nitrogen is surrounded by the electron pair. It's unshared electron pair. This is negatively charged, that's the electron pair, and electronegative atom bromine is there also, and hence this nitrogen is now surrounded by the electrons, and therefore it becomes very unstable. So immediately it loses this electronegative bromine atom to form a species in which nitrogen is surrounded by 6 electrons here. So see, this is the unshared electron pair. There is the negative charge, so 2 electron, and this bonding electron pair. So this nitrogen is surrounded by 6 electrons, and therefore this is the nitrine species. So in nitrine species, nitrogen is bonded to the carbon with a only single bond here. Remember, that's the important thing. And this nitrine species is very much electrophilic in nature, and it will undergo rearrangement. So rearrangement involves migration of alkyl group from carbon to nitrogen, and this unshared electron pair shifted here to form a carbon nitrogen double bond. And now if you see what the product you are getting after this rearrangement is isocyanate. So you get the RNCO. So this is the bonding present in this. So this isocyanate further hydrolyzed to form a carbamic acid, and this carbamic acid further undergo decarbonylation or decarboxylation, you can say. So this decarboxylation takes place, and this will picks up the proton here from the solvent to form the desired amine. Here we are getting the primary amine with elimination of carbon dioxide, and that carbon dioxide on reaction with base forms the sodium carbonate plus water. So this is the mechanism of Hofmann-Bromamide reaction. If you see the other examples of this Hofmann-Bromamide rearrangement, if you are taking the benzamide, it will give you aniline after completion of this reaction. If you have propanamide, your reactant, the product will be ethylamine, just the elimination of this carbonyl group. NH2 will join to this, you will get this ethylamine. Okay, so this is about the Hofmann-Bromamide reaction. Next method of preparation is by reduction. So these are the substrates which can reduced to amines by using simple reducing agents like lithium aluminum hydride or catalytic reduction in presence of platinum and nickel catalysts. So nitroalkanes can reduce to amines, nitriles, isonitriles, oximes and amides. All on reduction gives you the amines as a product. Let's see some examples. If you have a nitromethane and you are reducing this in presence of platinum or nickel catalyst, you will get the methylamine as a product. If you have a methyl cyanide, that's the acetonitride, on reduction, simple, that C triple bond N will be reduced to ethylamine. If you are taking the methyl isocyanide, then on reduction you will get the dimethylamine, that's the secondary amine, and if you are taking the methyl cyanide, you will get the primary amine, and that's the difference here. So cyanides gives you primary amine and isocyanides will give you secondary amines. If you are taking the oximes, that on reduction gives you primary amines here again, and if you are taking the amides, that is also after reduction with a strong reducing agent, that's the lithium aluminum hydride gives you primary amine. Now let's see the reactions of amines. In reactions we are going to see only one reaction here, that's the Hofmann elimination reaction. Now what is Hofmann elimination reaction? So quaternary ammonium salt on thermal treatment undergoes elimination to form a tertiary amine, alkene and water. Now in this Hofmann elimination reaction, usually less substituted alkene is formed as a major product. It depends on the different factors that we will see afterwards. But let's see this Hofmann elimination reaction. So here we have taken this secondary amine, and it is on Hofmann exhaustive methylation. So as it is a secondary amine, it requires 2 moles of alkyl halide to form quaternary ammonium salt. Now, why it is called as the quaternary? Because nitrogen is attached to 4 alkyl groups here, and therefore it is known as a quaternary ammonium salt. This quaternary ammonium salt on reaction with moist silver oxide forms quaternary ammonium hydroxide, which on thermal treatment, so we have to just warm it, so it will undergo elimination reaction to form alkene and tertiary amine. So here this OH minus picks up this proton here, and therefore there is a formation of carbon carbon double bond here. So ethylene will be formed as an alkene here, and the tertiary amine will be the other product here. So in this way you can say this Hofmann elimination reaction occur. So all of you getting it? Okay. Now let's see the Hofmann versus Sedzep elimination. How they are different, or how that Hofmann product and Sedzep products are formed. Okay. So what's a Hofmann elimination? Less substituted alkene is formed as a major product in the elimination reaction. While in Sedzep elimination, more substituted alkene is formed as a major product. And this orientation, whether it is a less substituted or more substituted alkene formed as a major product, decided by these two factors: nature, obviously, size of leaving group, and size of attacking base. These are the two factors that decides the orientation of the product. Let's see the example. Here we have taken the substrate. In this, X is the leaving group, and this substrate consists of two types of the beta hydrogens. Here is the beta, and it's a beta dash hydrogen. And when we are reacting with a base, you will get the two products. First is di-substituted alkene here. This is the Sedzep elimination, and here it is a mono-substituted. It's a Hofmann elimination. So as it is the less substituted, it is Hofmann, and is the more substituted, therefore it's a Sedzep elimination. Now, depending on the size of leaving group, percentage products of Sedzep and Hofmann are varied. If you have a bromine as a leaving group with a specific base, then its percentage of Sedzep product is 80%, while Hofmann is 20. But as soon as you are changing the leaving group to tosylate, size of leaving group is increasing, and therefore what happens, the base cannot approach this beta dash hydrogen easily, and therefore it prefer the beta hydrogen because it is a less steric interaction from the side, and therefore Sedzep product is now going to be decreased. So as tosylate group you are taking, if you are taking the SME2 group, so still bulk is now going to be increased, and therefore Sedzep product is now decreased. Now it's a minor. So Hofmann product now becomes a major here. And if you are taking this quaternary ammonium type leaving group, so NMe3, so then 95% you will get the Hofmann product, and only 5% you will get the Sedzep product, because the bulk or size of leaving group is increasing. Same approach you seen in the case of base. See here, base. So again, if you see the base, here we have taken the ethoxide ion, here tertiary butoxide, then you are taking this again a bulkier base. Here again size of the base is going to be increased if you are going from top to bottom, and as the size of the base is going to be increased, again same difficulty will occur here to abstract this beta dash proton, and therefore as the size of base or attacking bases increases, again percentage product of Sedzep is decreases and Hofmann is increases. So remember that. So these two factors are important here: size of leaving group as well as size of base. Okay. Now let's go for the next point, that's the electrophilic substitution reaction in case of aniline. So we are taking a case study here, aniline. So aniline, all of you know, it's a highly activated system because the unshared electron pair present on nitrogen, it shows the plus R effect. So it will delocalized in the phenyl ring and the system becomes activated. If you see this ortho position and para position, negative charge is present there. So that means ortho and para positions are more activated. So due to the particular delocalization of electrons. Okay. Now let's see the first reaction of aniline. It's a halogenation reaction. So aniline on reaction with halogen like bromine and chlorine in presence of water forms 2,4,6 trihaloaniline because of highly activated aromatic system. So product form are काय पाहिजे तुला स्वरा? First reaction, we are going to say it's a halogenation reaction. So aniline on reaction with halogens like bromine or chlorine in presence of water forms 2,4,6 tribromoaniline because both the ortho and para position are activated, and hence you are getting this 2,4,6 tribromoaniline as a product. But if you want the monosubstituted aniline, how we can do that? So for that we have to just control the activity of this NH2 group. How we can control that activity of NH2 group? Just by converting that NH2 group into a anilide group, NHCOCH3. So for that you have to just react aniline with acetic anhydride. So simple that acetic acid will be eliminated, that is CH3COOH, and remaining COCH3 group will join to NH. You are getting this acetanilide. Now this acetanilide group, this lone pair can be localized in the phenyl ring, as well as now it has a choice, it can go into the carbonyl group, and therefore NHCOCH3 group is now weakly activating group, weakly, and hence ortho and para positions get substituted. Let's see how they are going to be substituted. Here we have taken that acetanilide and reacting with the bromine in presence of acetic acid. So here ortho and para position, no doubt they are going to be brominated, but only mono substitution takes place. So here in this case para bromoacetanilide is a major product, while ortho bromoacetanilide is a minor product. So if you see here, this NHCOCH3 group is a bulkier group, and hence at the ortho position steric interaction is created, and therefore the percentage of ortho bromoacetanilide is less. Hence you will get the para bromoacetanilide as a major product. So this particular para bromoacetanilide on hydrolysis, finally you will get the para bromoaniline. So this NHCOCH3 group you can hydrolyze to aniline. So here in first step you are protecting this particular NH2 group by converting it into acetanilide, and then finally you are deprotecting here, so you get back to your amine. So in this way protection and deprotection strategies are used to achieve desired product. Okay, now let's go for the next reaction, that is nitration reaction. So in nitration reaction, aniline have to react with the nitrating mixture, that's the 1:1 concentrated HNO3 or concentrated H2SO4, forms a meta-nitroaniline. So why you are getting the meta-nitroaniline here, though NH2 group is ortho-para directing? Because this NH2 group, it undergoes a protonation in strongly acidic medium. So there is a formation of anilium ion, and now this anilium ion, it becomes electron withdrawing, and electron withdrawing group deactivates this aromatic system, and therefore you will get the meta substitution, and therefore the product you are getting here meta-nitroaniline. Obviously, in last step you need aqueous workup here, that anilium ion will be converted into a aniline by just abstracting this proton by base. So in this way, aniline on reaction with the nitrating mixture forms a meta-nitroaniline. If you want ortho and para products, usually para-nitroaniline, so how we can get that? So ortho and para-nitroanilines can be prepared again by controlling the activity of NH2 group, and how that activity is controlled already we have seen in the bromination reaction. Same you have to do here. So that aniline you have to react with the acetic anhydride to form the acetanilide. So now NHCOCH3 group becomes a weakly activated, and now it will undergo substitution at the para position, because at ortho position you will have a steric interaction. So the product you will get here para nitroacetanilide, which further undergo hydrolysis in acidic medium to form a para nitroaniline. So in this way you can get the para nitroaniline also, so by using or by employing this particular steps. So first protection, then do the reaction, and then deprotection by hydrolysis reaction. So in this way you can do that. Now let's go for the next reaction, that's the sulfonation reaction. So in sulfonation you have to heat the aniline with the fuming sulfuric acid to form para aminobenzene sulfonic acid. It is also called as the sulfanilic acid. So here we have taken the aniline, reacted with the H2SO4 at higher temperature 180 degrees Celsius to form sulfanilic acid. So thank you very much for watching this video. Please subscribe my channel Chemistry Basics and press the bell icon button so you'll get the notification of the next video. And if you like this video, please share and comment in the comment box. Thank you very much.